Hello friends, myself Chandra Kumar. I'm taking electrical machine design for final year students of electrical engineering. In the previous lecture, we are discussing the parameters related to the DC machines. Now we will discuss about the magnetic circuit calculation and the Carter's magnetic circuit calculation. This will be the part over where you are finding that there is a different parts are arranged over here with their notations. Number one, as the yoke. Yoke is the outer part of the machine. Two is the number of poles. P is indicated for the this one. There is a two poles are there. N, S, north and south, north and south. So it will be a four pole machine. Then there is a air gap. Air gap is in between the poles and the rotor part. Rotor is this one, and the gap between the pole, stator poles and the rotor, it will be called as the air gap. Naturally, the armature teeth. Number four will be indicated as the armature teeth over here. Then the armature core. Armature core, it will be this one. This part will be the armature core of the machine. Then there is a leakage flux. Leakage flux will be indicated by this one because some flux will be leaked over here. So this part is indicated as a leakage flux. AB is the mean length of flux path corresponding to 1 foot. And magnetic, then this will be the four-pole DC machine. There is a GNA. GNA stand for the geometrical neutral axis, and the A and B will be the path of this one. So that you are finding that this will be the path of the north pole to the south pole, and the circulation of the flux will be in the form of this one. So the different parts of the DC machine magnetic circuit or pole are yoke, pole, air gap, armature teeth, and armature core. Therefore, the ampere magnetic circuit is the sum of the ampere, that is AT by pole equal to AT yoke, AT pole, AT plus AT of air gap. Leakage factor or leakage coefficient is called the LC. All the flux produced by the pole will not pass through the desired path, that is the air gap. Some of the flux produced by poles will be leaking away from the air gap. So it will never touch to the uh, rotor pole, rotor part, so it will call as a air gap. It will call the leakage flux. The flux that passes through the air gap and cut by the armature conductors is the useful flux, and that flux that leaks away from the desired path is called the leakage flux. So phi p equal to phi plus phi l. Phi will be the main flux which we are, or the useful flux, and phi are indicated as the leakage flux. So as leakage flux is generally around 15 to 25% of the main flux. So phi p equal to phi plus this, so it will be LC cos phi, where LC is the leakage factor or leakage coefficient and lies between 1.15 to 1.25. Magnitude of flux in different parts of the magnetic circuit will be the flux in the yoke, flux in the pole, flux in the air gap, flux in the armature teeth, flux in the armature core, and the next will be the reluctance of the air gap. This will be the structure of the pole. Over here we are finding that this will be the yoke part, this is the pole, this will be the teeth of the rotor, teeth of the stator side, and this will be the flux distribution under a pole. So this will be indicator of the flux. And this will be the armature part, which will be the just below this one, and in between of that there is a air gap. So this will be called as the fringing flux, where the L dash G is more than the LG. Okay, LG is the length of air gap and T is the width over which the flux is passing in the air gap. Capital L is the axial length of the armature core. YTL is the air gap area or pole area per pole over which the flux is passing in the air gap. These are the some examples which we are discussing in this lecture. Over here, we are finding that whatever problem we are associated over that part, it will comes under this. So this will be the example one. If you are just look over there that if you calculate the ampere turns of the air gap of a DC machine given the following data, where the gross core length is given, air gap length is given, number of ducts is given, width of duct is given, slot pitch is given, slot opening is given, average value of flux density in the air gap is given, field form factor is this, Carter's coefficient is given for opening and air gap is equal to this. Carter's coefficient for opening gap length is 1. Now if the Carter's coefficient is given is greater than 1, then it may be kgs, kgv and for kg. If the Carter coefficient is less than 1, then it may be del s 1 minus del s del v or 1 minus del v. Therefore, kgs or kgv are to be found out to find out kg when the ratio BOS or LGO or BG close to 0, then it may be this one. So this will be the curve which will be given for the Carter's finding coefficient also for our calculation. Where over here ATG is given this one, Carter's parameter is given, kg is given, kt is given this one. So we can calculate the value of the kg. And after applying all these parameters, we know the value of the BV and the VLV. Del V is this one, and so that we can easily calculate the value of the KGV. So we can calculate the value of the finally we get the value of the KG and maximum value of the first density is equal to B average upon KF. KF we already calculated, and it will be this. So ATG it will be this. Next question will be the calculate the ampere turns required for the air gap of a DC machine given the following data. Gross core length is given, air gap length is given, number of ducts is given, width of each duct is given, slot pitch is given, average value of flux density in air gap is this. Field form is it. And Carter's coefficient for gap length, Carter's coefficient for the opening for gap length, and Carter's coefficient for the opening per gap length is it will be given. So as the previous question we are solving the same parameter we are discussing over this side, and with the help of the graph we can get the value of the BV and the LG, and on that basis we can calculate the value of the BV upon LG for the new parameter. So that new KGV will be given as this one, and we get the value of the ATG for the numerical form. Next will be the Carter's coefficient. Carter's gap expansion coefficient, where Kg is called the Carter's gap expansion coefficient for slots and is greater than 1. So SSSA equal to Lg upon lambda s L prime mu naught. AWS is the Lg upon Bt plus Bs L s L mu naught. So SAW and SSA, it will be the Lg. This equation it will be divided by this one. We are getting that. We can get the value of this one, and so that the AWS it will be comes out kgs times KSSSA. So this will be the Carter's equations and the equation which are written over there, and also discussing about the numerical. So we will continue this part in the next lecture. Thank you for attending the lecture.